Thank you for reminding me to record. Yeah, thank you. Good morning. So today we're going to talk about domains and ranges again. And if I have an algebraic equation, then what I want to do at this point, happy birthday, Kale, 17. Let's all unmute and sing her happy birthday because that's pretty awesome. Everyone, please unmute, and we're going to sing a happy birthday to Kale. So everyone who can unmute, unmute. Oh, come on. Happy birthday, Kale.
Happy birthday, bro.
If your microphone doesn't work, go ahead and just wish her happy birthday. Otherwise, unmute and wish her happy birthday, please. Oh, come on. This is fun. This is the fun part. That's awesome. Thank you for sharing that. Happy birthday. Okay, so when we are looking algebraically at domains and ranges, we are looking specifically for two things. So we are looking for when x is in the denominator. And when x is in the denominator, what we don't want is we don't want some number, say a divided by 0. If we have some number or some expression divided by 0, this is undefined. So we don't want when x is in the denominator, because when x is in the denominator, there is a potential for this to be undefined. So as an example, if I would have had x minus 3 over x plus 2, what I have to do is ensure that this x plus 2 is not equal to 0. So, the audio, okay, let's see if I can say it louder. Okay, so what I don't want is x plus 2 to be 0. That's the part I don't want. I don't want to be doing division by 0. So I'm going to set x plus 2 to not equal to 0, and I'm going to solve. So if I can solve it over the real numbers, that's going to tell me what my restriction is. So x cannot equal 2. So if x cannot equal 2, that is my domain restriction. So my domain restriction on this is not 2. So if I were to write the domain in interval notation, or set builder notation first, x such that x does not equal 2. Now with interval notation, you're going to start with negative infinity. You're going to go all the way to 2, get really close to 2. You're going to union it with 2 on the other side to infinity. So that's domain in terms of interval and set builder. Now, if you have something that looks like this, say you've got x plus 3 over x squared plus 16, once again, you want to make sure that this denominator does not equal 0. So you're going to set the denominator to not equal 0, and you're going to solve. Well, this kind of equation at this point is that it can, if you have a quadratic, you can factor with quadratics, or you can, with this particular quadratic, you can bring 16 to the other side. And what we have is x squared cannot equal 16, and that's a true statement. And I'm not going to do anything else to it. It's a true statement because x squared is never going to equal a negative number if you're in the land of real numbers. So because that's a true statement, I can't really solve, which means that this has a domain of everything. Is an element of the reals. Now, the difference between that one and say this one, g of x is equal to x plus 3 over x squared minus 16, is that this I can solve. So I have x squared minus 16 cannot equal 0. That means x squared cannot equal 16. That means x cannot equal positive and negative 4. So because it's a positive number, I can take the square root on both sides, and don't forget the plus and minus. So the difference is I can't factor f of x denominator. It doesn't factor over the reals. But on g of x, it will factor, and or I can solve by bringing the 16 to the other side, the negative 16 to the other side. So what you have to do when you see a denominator is you may have to factor it. Or in this case, because I just have two terms, I can just bring the numeric value on the other side of the not equals to and solve by doing the square root of both sides. So denominators is a big issue. The other place that we have to worry about is when x is underneath an index that is even. So when we have x under a radical where the index is even. And there are other cases that we have to worry about the domain, but that's going to come later in this quarter, so we don't have to worry about that right now. So again, what I have is if I have f of x is equal to the square root of x minus 3, then I set whatever is underneath the square root symbol, x minus 3, and I make sure that that is at least 0, so I make it greater than or equal to 0, and I solve. So x is greater than or equal to 3. So my domain in interval notation is 3 with an inclusive squared bracket to infinity. And my set builder is x such that x is greater than or equal to 3. I'm going to pause the recording, and I'm going to let you look at everything that we've done. Do it this way. And then I want you to ask me any kind of questions you have. So since there's no questions, then we're going to go back to these. And I believe I did D. So if you all on your pieces of paper, if you could do A, B, C, please. And I may just call on you. So if you don't put answers in either to the chat to everyone or to me personally, if you want to check your answers, I may call on you. So be prepared for that. Go ahead and pause this and let you all have the opportunity to work on these. Remember the recording this time. On A, I'm looking for those two things right now. I'm looking for x in the denominator or x underneath the square root. And because with A there is no x in the denominator, there's no x in the square root, then your domain for this will be everything. So negative infinity to infinity. Now if this is on the homework, the way in which you're going to type it in the homework in web work, and it does have a little link that says help intervals, and so you would type it with the parentheses, and then you do negative INF, and then you would do INF. So INF is for infinity in web work. So the domain in set builder notation is x such that x is a real number. There's no restrictions on that. Then if we take a look at, and I know that we want to talk about the range, so for right now, let's not worry about the range on these expressions, these functions, because the functions that are given from A through D, we're actually going to learn how to graph in this class. So we're going to leave A through D range for right now, because we'll spend more time in it later. So let's just worry about the domains A through D. Now when we have the graph, then we're going to really worry about the domain and range because we can read it off of the graph. But for A through D, let's just worry about the domain because, again, we will graph all of these later in the quarter and learn how to graph these. And then we can see the domain and range as we learn to graph. Okay, so for part B, this is kind of like my other examples, is that I've got x squared plus 4 has to be greater than or equal to 0. Well, when you subtract 4 from both sides, x squared has to be greater than or equal to negative 4. Now that's a true statement. Something squared is always going to be greater than or equal to a negative number. So because that's a true statement, I don't have to do anything further. And I just say, well, it's not going to factor over the reals, because whenever I see this, x or something squared and then plus something else, that is the sum of squares, and it never factors over the real numbers. it's your answers are always going to be complex. So when you go to factor this is going to be complex numbers, which we're going to learn about later in this class. But for right now, what I know is that it's not going to factor, because I end up with x squared is greater than or equal to -4, which is a true statement. It's not like in the previous ones where I had to do the plus and minus. It's a true statement, so I just leave it as is. So what that tells me is my domain and range on this is going to be exactly the same, or excuse me, not the range. The domain is going to be exactly as it was on my previous example. So -infinity to infinity, or interval notation of x, such that x is an element of the real numbers. So A and B, even though I have a square root, because it doesn't factor over the real numbers, what's underneath the square root, I ended up with a true statement, then I know that it's going to be everything. Because no matter what I put into for x squared, because I'm adding a positive number to it, it's always going to be positive. So there's no restrictions on the domain. I'm going to stop a moment and ask if anyone has any questions for me. So the question was, for A, how did I get the answer? Well, for A, I'm looking for specifically at this point only those two things. X in the denominator. I'm looking for fractions where x is in the denominator, and I don't see any fractions. And then I'm also looking for a square root. And so when I see A, I don't see any square root. I see x squared, but I don't see a square root. So the two things I'm looking for is a square root, or I'm looking for an index that is even. So the fourth root or sixth root or whatever. Because I don't see either one of those, my answer is no to those two questions. That means I have, because it's no, then I have no domain restrictions. So that means I get everything. So from -infinity to infinity, I get no restrictions. I don't have to worry about it. I can put anything I want in there for x, and a real number will come out. Now remember, I'm looking to make sure that this thing is a real number and that it's not undefined. So for A, answering those two questions both no means that we have no restrictions. Now, the other question that was asked was, can't I just do the square root over that? This is a really good question, and I'm going to take a moment to just talk about this in general. If I asked you to find the square root of 16 plus 9, well, by order of operations, it says I have to add those two numbers first. And the square root of 16 plus 9 is the square root of 25. The square root of 25 is 5. If I were to have tried to square root the 16 and the square root of 9 individually first, if I said, well, I think this might be equal to the square root of 16 plus the square root of 9, well, then this is going to be 4 plus 3. 4 plus 3 is not 5. So, and this is a good question to ask. When you see a square root, by order of operations, it says you have to do what's underneath the square root first. And because I have to do whatever underneath the square root first, that square root does not distribute over a plus and minus. So when you see the square root of x squared plus 4, this does not equal the square root of x squared plus the square root of 4, because it doesn't distribute over the plus and minus. So all I can do is say, okay, let's see what the domain is. And for B, because of the fact that for B, there wasn't any way to factor that over the real numbers, there's no restriction. Even though I see a square root, even though my answers to those two questions, do I see x in the denominator? No. Do I see a square root? Yes. Just because I see a square root doesn't mean I'm guaranteed to have any kind of restriction. And the same thing is true when I see x in the denominator. So if I would have had, say, h of x is equal to 5x over x squared plus 4, the same thing is happening here, that because it doesn't factor over the reals, there's no way I'm going to get 0 in the denominator. Because I'm not going to get 0 in the denominator, it doesn't factor, I'm going to get absolutely everything. So because I get absolutely everything, there is no restriction here, and so the domain on this is everything. What other kind of questions do you have for me? So I'm just going to erase this, and we're going to take a look at our last example before we do the graphing part. So in our last example, if you notice on this, I have not worried about the numerator. What we're going to learn later in this quarter is the numerator is going to force us to find x-intercepts. So I don't really care what's happening with the numerator in terms of my domain restrictions. Even if I have cancellations, I really don't care. What I care about is before I do any kind of simplification, if I would have had anything that would have canceled with a numerator, I mostly care what's happening with a denominator because that's going to determine my domain. So I ask myself again 2 questions. Do I see x in the denominator? And the answer is yes. So I don't even have to ask the second question initially. I can. The other question is, do I see a square root, a fourth root, or an eighth root? And the answer is no. So because I see x in the denominator, what I know is that this piece is what I care about. So I set that piece not equal to 0. So I have x minus 2 cannot equal 0. And this one's a nice easy solving. I don't have to factor it. It's already in its simplest form. It's linear. And so I get x cannot equal 2. So that is my restriction. From there, I'm going to build my domain, and we're going to learn about range later. And so for my domain, I can do it with set builder. Now, typically, you'll notice as we go through, when I see a restriction on the domain, a single number or 2, I typically will flip into interval or set builder notation because it's a lot less work. So the domain is x such that x does not equal 2. Now, the interval would start out with negative infinity to 2, and then with that 2, you're going to use a parenthesis. That means you're going to get really close to 2, but you're not going to get 2. So you're going to have something really close to 2, union with 2 to infinity. And so that's what it would look like in interval notation. What kind of questions do you have for me on that one? On the next type of questions, we're going to be looking at graphs, and this is where I will care about the domain and range. So I'm going to do an example over here first, and then I'm going to have you all try the ones that are on the notes. So if I have this function, say I'm going to start out with here, and I end with a closed dot. Now, let's make this, I want to make this so it's clearer where the bottom starts. When you're reading a graph, you're going to read your domain from left to right. So you're going to read the domain from left to right. And what you're looking for is the first time you see the graph. So the first time I see the graph is right here. So I go up here, and this is my starting point. So let's just put a number on there. Let's make this -7. So that is my first time I see my graph in the domain. Now, I look to see the last time I see my graph. The last time I see my graph is right here. So I go down to the x-axis, and let's call this 10. So my domain, as I read from left to right, is from -7 non-inclusive. And it's non-inclusive because I have an open dot. It's non-inclusive. And then the last time I see my graph is at 10, and that is inclusive because it has the closed dot. Now, when I'm reading my range, I read from bottom to top. So I look to see reading from the bottom to top. The first time I see my graph is right here, as I'm reading from bottom to top. So from there I go over to my y-axis, and let's call this -5. And then the last time I see my graph is right here. So I go across to the y-axis, and let's call this, say, 3. Not drawn to scale. So my range on this starts from the bottom of the graph, the lower part of the graph, and it is an open -5, and the last time I see it is a closed 3. What kind of questions do you have?
Could you clarify again what the parentheses and what the brackets mean?
Absolutely. So whenever you see an open dot, that means it's not included. That means you get to get close to -7, but you don't get to include -7 in the domain or range. If you see a closed dot, that means you get to include it, and that's the bracket. So in terms of inequalities, like if you would have done on our previous examples where I had a restriction in the domain, I get to get close to, but I don't get to include it. So if I take a look at this one right here, I wasn't allowed to have the number 2. Because I wasn't allowed to have the number 2, that's how come these are non-inclusive. Does that help?
Yes, thank you.
Yep, absolutely. Any other questions you have for me on this? And no, if we haven't got to, the question is on the thing is on my chat is, if we haven't got to 3 and 4, no, it won't be due on Monday. I'll just push it back. I have to set the due date for these, and I thought, ooh, we might get to that. We're not. That's okay. We'll get there. We'll get there when we need to get there. So I will change. Don't worry. Any of the quizzes that are associated with 1.3 and 1.4, if we don't get to them and we don't finish those, then those will also be pushed back into the next week, which means the later quizzes will also be pushed back. So don't worry that all of the quizzes are aligned to the things that we should be covering. So you may find that some weeks you have only 3 quizzes. That's okay. We'll get there. Okay. Any other questions before I have you all do the quizzes? Quizzes. Have you all do the domain and range from the graphs? Any other questions you have for me? Okay. So here are the 2 graphs. And can you all see whether or not they're open or closed dots on those? If you can't, please let me know. I'll just make them as they are. So this is a closed dot. This one is a closed dot. This one's a closed dot, and this one is an open dot. So go ahead and do the domains and ranges on those, please. Let's go ahead and go over this. So as you are reading your domain, you always go from left to right. And the first time you see your graph for the domain on the first one is inclusive of -4 because it has the closed dot. And then the last time you see it is at +4, and it's also a closed dot. As you read your range, you start from bottom to top. And the first time you see your graph is at 0, which is inclusive. And that's because both the left and the right side have the inclusive. Now, if one had the inclusive, one did not, that's okay. One of them has the inclusive, so that means I would have included it. And then the last time I see it is at the number 2. Because this part of the graph is a nice smooth curve, right here in particular, the highest point is a nice smooth curve, and there's no hole there, so that's why by default I get to have the number 2. Had there been a hole right there, let's make a really big hole right there, then I would not have included the number 2. It would have been a parenthesis. But because that hole is not there, then we have inclusive. As I read the domain from left to right on my next graph, my domain, the first time I see my graph is at -3, and it is inclusive. The last time I see my graph is at 2, but it's an open dot, so I didn't get to include that. On my range, the first time I see it, again I read from bottom to top, is at -5. It has a closed dot, so I get to include it, so -5. And the last time I see it, as before, I have a nice smooth curve, is at 4, and it is inclusive. So there is your domain and range on those 2. I know we're out of time, but I'm going to ask, what kind of questions do you have for me on these? No, the homework for 1.3 and 1.4 in WebWork and any quizzes that are associated to those will be pushed back to next week, the following Monday, because we just haven't got to them yet. Any other questions you have about these, though? The worksheets? You mean the... Oh, the notes. Yes. Let me show you really fast where to find the notes. And Benjamin, I see you raised your hand. So if we would have had something that would have, say this one would have done something like this, it would have gone all the way down like this with an arrow. Then if that would have been an arrow, that would have changed two things. It would have changed the domain here. So if that would have gone down forever with an arrow, then your domain would have changed from -3 to infinity. Because as you read it, even though it's going down, your x's are increasing, so it's going to infinity. The other one, right here, this would have changed the range as well. It would have changed it from -infinity, because you notice reading from bottom to top, the lowest is -infinity, but it would have maxed out at 4. So if you see an arrow there, it will change your domain and range. And if you have any questions, go ahead and send them through Canvas. Remember, I do have office hour today at 12:30 to 2. So you're more than welcome to come in and ask any kind of questions you have on anything that we're doing, or homework questions or quiz questions. Come on in, 12:30 to 2 today. Otherwise, you all have a great day. And we only have a little bit left on this, is the piecewise. Piecewise, well, that's more than a little bit. We'll address piecewise tomorrow. Have a great day. Thank you all.